No. Today only models which are originating from porous media flow. Tomorrow I will talk about. All right. So first of all, thank you to the organizers for inviting me over. It's just that when I went through the program, I realized that people are talking about two-scale convergence, multiscale modeling, compensated compactness, periodic unfolding. So there is nothing much left for me to talk about it. So I sort of decided that I can present various models that I worked with through my academic career, where I implemented the concepts of micro-macro modeling, homogenization theory, and also tools from applied analysis to analyze these models. So I will present a series of models, and you'll see how the concept of both mass action kinetics, multiscale modeling are coming together. So to begin with, okay, now it's working. Okay, so just to give you a small motivation about this multiscale modeling is that during the late 60s or early 70s, when engineers were trying to make some new materials, the idea was to mix 2 or 3 materials together to come up with a new material that is more durable and it has more longevity. But in order to analyze the overall behavior of this new material, you have to sort of categorize this new material into different scales. So for example, here you can visualize this concrete or this plywood or even soil as a multiscale material. So when we talk about categorize this new material or composites, you always have to think about the microscopic scale, where you can describe the heterogeneities very precisely. And it can also give you a really nice behavior, I mean, what is happening at the microscopic level. But at the same time, these microscopic models are not good for conducting numerical simulations. It's not feasible. And therefore, you need the macroscopic description, where you can describe the global behavior, or sometimes we also call it as average behavior of the medium. The size could vary from centimeter to kilometer, and since you have removed all the heterogeneities, it will be very good for conducting numerical simulations. So we needed to have a microscopic description as well as the macroscopic description. So in order to analyze the heterogeneities, it's always important to have the model at the microscopic level. But to do the numerical simulation, you have to go to the macroscopic level. Now, to establish a bridge or a channel from micro model to the macro model is something what we term it as homogenization. So homogenization is a tool that will give you a macroscopic or a continuum, or sometimes also called as upscaled or averaged behavior of a medium which is microscopically heterogeneous. So, for example, in this case, suppose this is our a heat equation for the steady case, and we assume that U epsilon is the temperature distribution, x represents the macroscopic variable, and xy epsilon is representing the microscopic variable. And if you denote the diffusion coefficient, d epsilon, in this fashion, and when you try to plot it by taking the domain omega from minus pi to pi, so I don't know if this figure is visible or not, but if you see, then for epsilon equals to 0.04, we have a global oscillation in the diffusion coefficient, but at the same time, we have the micro oscillations as well. And if you make your epsilon smaller and smaller, then basically you are decreasing the micro oscillation, and you have overall the global oscillation. So that means by making epsilon go to 0, we are sort of getting rid of these micro oscillations. That means we are homogenizing our given diffusion coefficient. That means it is giving us the averaged, or how to say, global behavior of the of this diffusion coefficient. So this is what we mean by homogenization. Yes. Yeah, exactly. Yeah, d of x. Yeah. Okay. Yeah, that's clear. All right, so basically when we are doing the epsilon going to 0, we are homogenizing the material. But the issue is, when we say epsilon is going to 0, what do we actually mean by it? So when we are saying epsilon is going to 0, we are somehow saying that some kind of limit. So you are doing epsilon go to 0, so u epsilon, the solutions of your given equation in this case, they will converge somewhere. So we are talking about some sort of limit abstractly. So if we talk about the limit, then there will immediately several questions arise. So the first question is whether these u epsilon that they will converge to some limit. If it is converging to such limit, then in what sense or in which function space that limit exists, whether the limit will solve some kind of boundary value problem, or whether it will solve an exactly same type of boundary value problem or not, where your u epsilon we're solving. What can we say about the diffusion coefficients, because our d epsilon were also depending on the scaling parameter epsilon. And finally, when you are doing the averaging, the averaged or the upscaled u is a good approximation to your u epsilon or not. So whether the homogenization is worth doing. So all these questions can be answered step by step when we are doing the homogenization. So in reality, we know that a natural porous medium or a natural multiscale material is actually, they have very complicated structure. So for example, here, in case of these pellets or the sponge or pieces of rock, they can be considered as a porous medium. But here, the solid matrices are connected with one another. They are not periodic. So in general, a natural porous medium is non-periodic, as well as it can have connected solid parts. However, for us to do the homogenization, a very natural assumption is to assume that the given porous medium is periodic. And this is the most realistic assumption that you can make on your porous medium in order to perform the periodic homogenization. So from here and onwards, we assume that, first of all, the solid parts here, they will be disconnected from one another. And at the same time, they will be periodically distributed all over your medium. So these are all periodic settings before we can actually jump into the problem. And to visualize, let us assume that the given porous medium is denoted by the domain omega, and we have a representative cell Y. And in this representative cell Y, we say that these white spaces, they are the pore space, and this YS, the dark gray region, are the solid parts. So you have pore space and you have the solid parts. And for a scale parameter epsilon, we make this kind of substitution, that x equals to epsilon y. So when your epsilon is half, then your representative cell will look like this. When your epsilon is 1/4, this solid matrices, they will become smaller. When you make epsilon 1/8, then it will become further smaller. That means when you are making epsilon go to 0, literally there is no difference between the solid part and the white space. So if you visualize this solid matrices as a black balls and white spaces as pore space, then when you are making epsilon go to 0, you are basically obtaining a gray medium. So that gray medium is actually your homogenized medium, the medium which you are actually approximating your given heterogeneous medium. All right? So what we are doing is we are basically saying the pore space, they will be covered by the translated versions of the cell epsilon py, epsilon yp, sorry. And the solid parts, they will be covered by the translated versions of these epsilon times ys, and whatever remains is the boundary. So this is what the periodic setting would look like. So basically, if this is your given, let's say, domain omega, then when you are doing x equals to epsilon y, then it will start look like this. And when you do the reverse substitution, then you are again back in this, this bigger solid parts domain. And another assumption is that the white spaces, they will be connected, whereas the solid matrices are disconnected. That's what we started with. So having these many periodic assumptions, I would say, now I'm going to introduce several models where we will see how we are doing the modeling. So this is the very first model. basically motivating from diffusion reaction of chemical species. So suppose we have a given porous medium, and in the white spaces, these red dots, they represent the mobile species. So you can have as many number of mobile species as you want. And all these mobile species, they go through diffusion and reaction processes, and all these reactions are assumed to be reversible. So for example, here, if you say Xi's are your chemical species, then your jth reaction will look like this. So tau ij and nu ij, they are called as the stoichiometric coefficients. So that means our reactions, one particular example could be, suppose A plus 2B equals to some C plus D. So we have one reaction in this case and 4 chemical species. Based on that, we will have 4 reaction rate terms for every chemical species corresponding to one chemical reaction. An example could be, let's say, Na plus Cl is equals to NaCl. So here you can have chemical reaction rate for reaction rate term for Na and Cl, and basically I will show in the next slide how we can write down the reaction rate. This one is reversible, yeah. Yeah, if you, I mean, maybe not. So I'm not very familiar with chemistry, but any type of reversible reaction that will fit into the fit into this structure. You have to, yeah. Exactly. So I'm saying that any type of reaction like that, yeah. These are? Yeah. Or you can do that H2SO4 example. If you're not happy with this one, then there is another example, H2 plus SO4 one, which gives you H2SO4. I know this one is reversible. Yes. Yeah. Huh? Yeah, it doesn't. So what I'm saying is any reversible reaction can fit into this structure. Now, I take Sij equals to, so small Sij equals to difference of these two, and they are called as stoichiometric coefficients. And based on that, I will denote a stoichiometric matrix as this one. Now, since I have assumed that we have I number of mobile species, I'm assuming that U epsilon I is the concentration of ith species. So basically, we will have a system of equations. So every chemical species will have a diffusion reaction equation. So basically, we are dealing with a system of diffusion reaction equations, and this SRU epsilon is the reaction rate term. So since we have the mass action, we have the reversible reaction, we can model this reversible reaction using something called mass action kinetics. And mass action kinetics says that the reaction rate term can be represented as the forward reaction rate minus the backward reaction rate. Whereas the forward reaction rate, as you can see here, we have the product of concentration of I chemical species, right? So we have U epsilon 1, U epsilon 2, U epsilon 3 up to U epsilon M. U epsilon I. Now these SMJ, if we go back, these SMJs are basically the difference of stoichiometric coefficients. That means these, they can be as large as we please. So basically here SMJ can be as large as we please. And this says that not only you have the product of concentration of species, you also have their exponents. So that means here this term and this term, they are highly nonlinear. So it's not only a system of diffusion reaction equation that will be important to study. At the same time, we have a highly nonlinear reaction rate term in our model. And we are assuming that all these phenomena, they are happening in the pore space of the given porous medium. So our first task would be whether we can talk about an existence of solution. So this is a system of diffusion reaction equation. So what can we say about the existence of solution? And whether that solution is unique or not, whether it is positive, and most importantly, whether we can talk about a global solution. So we were, primarily interested in the global solution. So what can we say about the global existence? And once we had the existence, whether we can upscale this model from micro to macro scale. In the homogenization community, it is well known that if you have a nonlinear term, then you need some kind of strong convergence to pass the limit. So it doesn't matter whether you have L2 setting or LP setting. If you have a nonlinear term, you always try to obtain some kind of strong convergence for the solutions so that you can pass the two-scale limit. So all these things can be answered for this model. So first of all, to analyze this model, I said that we have I number of species. And from literature, it is very known that if all of these Ds, if you have different Ds, that means if you have different diffusion coefficients in your system, then the global solution does not exist. Even till today, at least I don't know that there are any results which can talk about global existence of solution for different diffusion coefficients. So this is a very, important result that in this case, we assume that all the chemical species, they have the same diffusion coefficients. And that was a major assumption or a major compromise when we wanted to show the global solution. So we started with that all the diffusion coefficients are same. And if we do that, then these are our usual Sobolev spaces and dual space setting. And this one is the real interpolation space based on which I defined my solution space. And the norm on this space will be defined in this fashion. And since we are dealing with vector basically a vector U epsilon, which is the vector of concentration of all the chemical species, we also have to define the norm on this I tupled or vector valued function space. So the I tupled norm is defined as the sum of the I norms, basically. All right. So now, based on which I can talk about the weak formulation. So the weak formulation is given in this way. All right. And in theory of parabolic equation, we know that if you have, let's say, x and y as the two Banach spaces, where y is densely embedded in x, then this x in this interpolation, real interpolation space, will actually be the trace at t equals to 0 for functions in this space. So you remember in parabolic equation theory, when we dealt with this kind of equation, and we had equals to u0, and we say that the solution u exists in where we had u0 in H1. So this is from our classical parabolic equation theory, that if you have a diffusion reaction equation or let's say Cauchy equation in this form, then we say that the solution exists in this space. That means u is in H2 and the derivative of or the u dash is in L2 when you have u0 in H1. So this is nothing but the application of that trace theorem, because this trace theorem says that for t equals this trace theorem says that for t equals to 0, u0 will belong to the interpolation of this one and this one. So our u0 will belong in the interpolation of this one. And if you calculate this interpolation space, it will actually be H1 of omega. Yeah, here we have to take half and here we have to take 2. So so far we were directly taking this, but the idea behind taking u0 in H1 is actually that theorem. And in general, we can write like this. So if your S is if your S is given by 1 minus theta times S0 plus theta S1, then this real interpolation space is equal to this Besov space. And if you plug in theta equals to half and I don't know, S0 equals to 2, S1 equals to 0, then you will basically obtain this Besov space B2, B12, that is your H1 space. So that's the idea behind taking the initial condition in this interpolation space. And we also needed another tool from parabolic theory that also from parabolic equations, we know that whatever space you consider your function belongs to, the time derivative will always be one space less regular. So that means if your f is in L2, your u dash will be in H minus 1. So always u dash, the time derivative of u, will be one space less regular. So this particular property says that if you have your Cauchy equation or in this format where A is your closed linear operator, which can be our elliptic operator, then this equation will have a unique solution for every f in LP of Sx. So that means if f is in this space, then from here our time derivative is also in the same space. That means your time derivative will also be in the same space as your function f is, and hence the term maximal. So maximal parabolic regularity. So we are saying that the time derivative is as regular as the function itself. And if our operator A has that property, then we can say that this equation, this Cauchy equation with initial condition u0, will have a unique solution, and it will satisfy this inequality. And of course, for that, you need your initial condition in this space. So this particular property is called as maximal parabolic regularity, which guarantees that if your function f is in certain space, then the time derivative of u will also be in the same space. It will not be one space regular, one space less regular. So we needed this tool as well, and these are some technical lemmas. So our elliptic operator has a maximal parabolic regularity, and these are some embedding theorems which we needed somewhere down the line to prove some results. So I will just skip that for the time being, and I will come back to our first question, whether we can talk about existence of global positive unique weak solution. So first of all, the positivity can be shown by Grunwald's lemma, and in order to obtain the global solution, we took help of something called Lyapunov functionals. So Lyapunov functionals have very nice properties, and so we construct the Lyapunov functional. So first of all, we define a function gi, and based on this gi, we defined our function g, which is sum of these gi's. And with the help of that g, we defined a function f, which is finally used to define the function capital F. So we defined small gi's, with the help of which we defined g, and that one we are using to define f, and if with the help of f, we are defining this capital F. And from this definition, it's very much straightforward to obtain this inequality. So concentration of each species will be basically dominated by this G. Now this G is used to define a small fr, and a small fr is used to define capital Fr. So that means if you take the rth power on both sides and use the integration sign, so left hand side will be your right hand side will be your LR norm on this domain omega epsilon, and right hand side and this side, the left hand side, will be Fr of u epsilon. So basically what we are saying is, initially we started with a very highly nonlinear reaction rate terms, which has the product of concentration of species with different powers and all. Now if we can obtain an upper bound for this capital Fr, so we have something like norm of ui Lr omega epsilon P is lesser or equal to capital FR. Now, if we can obtain an upper bound for this C, if we can obtain an upper bound for this capital FR, then this R is any natural number. So we have chosen this R as any natural number. Where is that? So R is any natural number. So if we can obtain an upper bound for this Uis, then what we are saying is that you can choose your R as large as you please, and since your reaction rate term is a product of U epsilon 1, U epsilon 2, for example, let's say if our reaction rate term looks like this, U epsilon 1, U epsilon 2 minus U epsilon 3, U epsilon 4. So you can choose your R power as large as you please so that we can use the Holder's inequality and make this reaction rate term belong to any LP space we want. Right? So you can take L2 norm here, then it will become L2 norm, then you can use again the Holder's inequality, then you'll end up with some L3 by 4 and something like that. And then you choose your R as large as you please so that you can make the whole reaction rate term to be bounded in any LP space as you want. So if we can be able to show that Ui's are bounded by some Lyapunov functional, which is bounded by some constant C, we can control the highly nonlinear reaction rate term. We'll have a good grip on that term. And that was the overall idea, to obtain an upper bound for this FR. And in order to do that, we use something called Schaeffer's fixed point theorem. I will not go into the technical details, but using Schaeffer's fixed point theorem, we can be able to obtain an upper bound for this capital FR, and that will be, of course, independent of epsilon, and then that will act as an upper bound for these Ui's, and then you use Holder's inequality to say that your right-hand side will always be bounded. It doesn't matter whatever LP space you choose R big enough, and then your right-hand side will always be in that LP space. And if the right-hand side is in LP space, if our right-hand side, which I'm denoting by F of U, not SR of U, is in some LP space, then we know that LP is embedded in H1 P dual. So from here we can write that F of U is in some LP of S H1P dual, and that means our F is in LP of S H1P dual, and U0 is assumed to be, in real interpolation space, and therefore we can use the maximal parabolic regularity to show that we have a unique solution. Because our operator, the elliptic operator, has maximal parabolic regularity, and we managed to show that F of U is in this dual space setting. And therefore, we have a unique positive, so far, solution. And that is global also, because this estimate is global in time. So it's the theory of evolution equation, Lyapunov functional, they are both coming together. And with the help of which we managed to show that the system of diffusion reaction equations have global positive weak solution. And the uniqueness, it will be shown by Grunwald's inequality. So that was the very first model that I worked on, and it deals with basically a system of diffusion reaction equations. Now that we had the existence of solution, we also needed to obtain, the second task was to obtain the upscaled model or homogenized model. So one method was to use the asymptotic expansion, which was not that much interesting to us because we sort of wanted to have two-scale convergence. So we wanted to address the homogenized model more from two-scale convergence point of view. And I'm pretty sure throughout this workshop, you may have got the definition of two-scale convergence. So We define it as a sequence of function is set in this space is said to be two-scale convergent if it satisfies this definition. And these are some results that if your sequence of functions are strongly convergent, then you can say that they are also two-scale convergent. And if your sequence of functions are weakly convergent in this space, then your function u and the gradient of u will converge to this. So u epsilon will converge to u, and gradient of u epsilon will converge to this. So these are the two classical results from two-scale convergence. Now, as I was saying, that we were able to obtain this a priori estimate, which was independent of epsilon and also global in time. So using this estimate, we can show that our u epsilon and SR of u epsilon will be strongly convergent. There are some technical calculations, but it's nothing, detailed theory going on. So just doing some simplification, we can be able to show that our u epsilon and SR of u epsilon are strongly convergent. And then we choose some functions, test functions phi 0 and phi 1. And we multiply our system of diffusion reaction equations by these phi's. And then we pass the two-scale limits. So we know that this gradient of u epsilon is weakly convergent, is two-scale convergent to this one. We know that SR of u epsilon is strongly convergent to SR of u, so we can pass the two-scale limit. And ultimately, our upscaled model or homogenized model will look like this, where the P's are defined with the help of cell problem. So having this estimate was the main important point in this whole analysis. So once you have that estimate, everything will just follow in a very standard way. And now, then I started looking into a bit different type of models. So for example, here in this case, in case of oil reservoir, you push water so that your oil can be pumped forward. So basically, in case of oil reservoirs, you have these solid parts as sand grains, and these small black dots, they are the oil droplets, and the blue part is basically water. So we consider the evolution of a mixture of two incompressible, immiscible fluids. So we say that both water and oil, they are incompressible and they are immiscible. So one is floating on another. And in a more natural setting, you'll have oil and water here and there distributed. But we are assuming that there is a layer that is separating. So beyond that, upper part of that layer will contain oil, and the below part will contain the water. Because for the natural setting, we didn't know how to do the modeling part because you have oil, water scattered everywhere. So for the time being, we assume that there is a global layer that separates the water from the oil. And we say that U epsilon is the microscopic concentration of the oil, and mu is the viscosity, lambda is the interface. So the width of this interface is denoted by lambda, and Q epsilon is the Stokes velocity, based on which our Stokes-Cahn-Hilliard equation will look like this. So this is basically the Stokes equation. That's the surface tension term, and this is your Cahn-Hilliard part. Where our small f's are defined as the derivative of capital F's, and the capital F's are called as the double well potential energy functionals, given in this way. If you are interested more in the modeling, I would suggest to look into my paper if you would like. Now this is the model at the microscopic level, and then again we used the classical theory from evolution equation to show the existence of solution and uniqueness by Grunwald's lemma. And then we use some energy estimates to obtain this energy method to obtain this a priori estimate. So this is also very classical results, so it wasn't that difficult to obtain these a priori estimates. And once you have this, we can talk about the convergence, two-scale convergence of all these parameters that are involved here. For example, U epsilon, Q epsilon, W epsilon, and we will have the two-scale convergence of all these terms involved in the model. And at the same time, we can show the two-scale convergence for the derivative of the double well potential, the surface tension term, and the product of Q epsilon and U epsilon. And based on which, this is how your upscaled model will look like. At the last, okay, perfect. That's also will do. Now, the third model where I implemented this homogenization concept was a situation where not only mobile species, on the surface of the solid parts, you can also have some kind of crystals or immobile species present. Now, that crystal can dissolve in the fluid, hence dissolution, or the reaction can happen on the surface of the interface, and that immobile species will accumulate on the surface, hence precipitation. So you can have dissolution or precipitation, which was the third, which is the third point here. So I start with the same assumption that I have I number of mobile species, and they all go through diffusion and reaction. Whereas in this case now, you also have some crystals or minerals or immobile species, whatever you want to call, they are present on the surface of the solid parts. And all these reactions, they are reversible. So the reaction amongst the mobile species is reversible. At the same time, this precipitation and dissolution. So when the chemical species are reacting at the surface, you have the precipitation, but at the same time, the substance which is present on the interface, it can dissolve, and it will give you the mobile species. So you have dissolution. So both precipitation and dissolution, they are assumed to be reversible in this case. So like before, our reversible reaction for the mobile species will look like this, based on which we can model the diffusion reaction. We can model the governing equation for the mobile species. So in this case, it will be the similar as before. So we also included the advection term, and SRU epsilon is the reaction rate term as before. Now here on gamma epsilon, if we go back, I'm saying that on the surface of the solid parts, due to the presence of these minerals, you can have these minerals dissolving, and then this will give you the mobile species. Whereas the mobile species, they can react on the surface, and it will give you minerals. So basically, some kind of flux or some kind of exchange is happening at the interface. So in our boundary condition, on the surface of the solid matrices, you'll have some kind of flux condition. And that flux condition is nothing but the reaction that is happening on the interfaces, which is given in this way. So now, how do we model the reaction at the interface? So basically, we are saying that the mobile species, when they are reacting, all the immobile species, when they are reacting, they are giving one molecule of the immobile species, and when these immobile species, when they are dissolving, they are giving all these I number of mobile species. So dissolution, precipitation. All right? And from a very well-known modeling technique of Knabner and Van Duyn, they say that the dissolution especially is modeled by some multi-valued functions. So we are saying that when there is some kind of substance present at the interface, the dissolution rate will be constant. So the dissolution will take place always. But when there is no substance present, then in that case it will, or when the substance, when the concentration is less than 0, which is practically not possible. So we assume that the dissolution rate is 0, and when it is 0, then it lies between 0 to 1. So that's the dissolution part, and the reaction rate term for this side is given by precipitation, which is same as the mass action kinetics. So even in case of mineral reaction, we have forward reaction rate and backward reaction rate. So this is the forward reaction rate going this way, and this is the backward reaction rate coming this way. All right? And for the immobile species, for the minerals that are present on the interface, since they are not going through any diffusion, we'll basically be having an ODE, and the rate of change of, concentration of immobile species is given as the reaction rate term, which is given by this here, the precipitation minus dissolution. And now we can model the entire situation by substituting for this minus of duy epsilon here. So here it will be basically precipitation minus dissolution term, and you have the OD for the minerals. So we have the diffusion reaction equations for the mobile species, and we have the ordinary differential equations for the immobile species, complemented with some boundary conditions, of course. So this is the case when we assumed that even though some kind of mineral is dissolving, it is giving you mobile species, or mobile species are reacting, that is giving you minerals. We always assume that the interface is not moving. But realistically, if you visualize, when they are going through dissolution, the interface will become smaller and smaller, but when they are precipitating, the interface will become bigger and bigger. So you are basically in a situation of moving boundary problem. And that is more realistic situation, right? So here in this case, I say that these gray parts, they are solid parts, but these light gray regions, they are the minerals. So either they are dissolving or they are precipitating, and then our boundary is moving. And if the boundary is moving, then from the tools developed by Sethian and O'Shea, they actually tackled moving boundary problem in a very nice way. So they said that instead of focusing on the moving boundary, you can write the moving boundary in terms of a level set. And now you focus on the level set instead of focusing on the boundary. And at any time, if you want to know the position of your of the moving interface, you just look at the level set given at that particular time, and that will give you the position of the interface. So here also we implemented the similar concept. So we are saying that the interface is moving, and the movement is always the movement is always in the direction of the normal. So the interface, I mean, if you want to know how the movement is happening at a certain point, you always think the interface is moving along the normal, not in an inclined way. So it is always happening in the direction of normal. And another tools that we applied here is that we wrote down the interface in terms of the level set function phi. And if you write down the moving interface in terms of zero level set phi, then the equation for this interface will be given by this first order hyperbolic equation. And now, this is how our whole model will look like in case of moving interface situation. So our diffusion reaction equation for the mobile species will remain as it is. That one we are not touching. But on the interface of the solid parts, whatever is happening is modeled via this level set function. All right? Where this V epsilon is nothing but this reaction rate term, which is given by dissolution and precipitation. Then again, we showed the existence of solution, and for the homogenization, we took help of asymptotic expansion, and we were successfully managed to show the upscale or obtain the upscaled model using asymptotic expansion, which sort of looks like this. So as I was saying that ultimately we will have, after the upscaling, we will have basically a system of diffusion reaction equation and an equation for the a level set equation, upscaled equation, of course, for the moving interface. And all these other terms, we are not bothered by that. And for this, we could be able to show the existence of unique positive weak solution in some appropriate Sobolev space setting. Yeah, it is a parabolic hyperbolic system actually. So this one is the first order hyperbolic equation. That's your regular parabolic equation. Yes, that's a good point actually. So what is happening is, yeah, it can develop some corners. So basically, this is our, let's say, representative cell Y, and this is our solid part. So if the precipitation is happening, then your solid parts will start growing, and at some point it will block your entire porous medium. So then nothing will happen. So we also did some numerical simulation where we set up a time that after which the entire porous medium will simply get blocked. Basically, we say that, I mean, in the simulation, we say that after this point, so we set up all these parameters, D and whatever involved in there, and we took a very simple reaction rate term, and then we did the simulation, and our simulation can show that, I mean, if the precipitation is keep on happening, if the rate of precipitation is more than the rate of dissolution, then at some point, this whole region will get blocked. Or simply, if I don't consider any dissolution, if I only consider that there is a precipitation, then our simulation can show that after a while, this will sort of block the entire porous medium. Exactly, yeah. No, we are using fixed point argument. I know viscosity solution is there, but we didn't use viscosity solution for hyperbolic equation. All right, and then I worked on another model, which was motivated from transmission in the metamaterials. So basically, nowadays, metamaterials is something that you create by mixing 2 or 3 materials together. And in semiconductor devices or in nano-optics, when you pass a light wave or a signal, then how it is being received on the other side of that semiconductor, it's very important. I mean, so how to say, the faster it goes, I mean, the better it is, basically. So here, if you consider this slit as a metamaterial, and if you consider some kind of source or the light which you are sending through this metamaterial, and here you have the image, basically it will go through all these, so this, the dots are basically the hollow parts, so through which it will not travel. It will travel through these yellow parts actually. So it will go in some kind of zigzag motion. So basically, if you look at the microscopic level, then you can see it as it is forming some kind of how to say a curved structure. So I can visualize it as a curve, or what is the right term? So it is forming something like some kind of slit, basically. So if I have, let's say, 2 columns of holes, so basically we have something like some kind of how to say, ribbon-like structure through which your ray of light can pass through. And basically, we wanted to obtain the effective or the upscaled behavior, the effective behavior of this metallic layer, and also the effective behavior of the permittivity of this whole medium, that how it is behaving. So the overall modeling is a little bit how to say technical, but ultimately we will obtain a Helmholtz type equation. So basically we have these electromagnetic waves that are passing through these slit kind of structure, and from there we'll end up with equations of Helmholtz type, where your A etas are given in this way. So if we consider this slit, then our A eta will be given in this way, And if we are outside this slit, then it is basically 1. So the model. Yes. So this is the model basic. So we are considering the light waves or light beams that are passing through this material. So this is our given metamaterial actually, which is composed of. Okay. So basically, we are saying that this material which you have ultimately here, this U eta are actually the light, is the concentration, or how to say, is representing the concentration in some way for that light wave that is passing through this this slit. And
I suspect some abnormal behavior.
Abnormal behavior like how?
What is the difference between wave propagation and ordinary behavior? Wave propagation better.
Yes, so that particular property will be analyzed, though imposing some condition on this epsilon r. So this epsilon eta, the permittivity is given in terms of this eta is basically the scaling parameter times epsilon r, and if you impose that this epsilon r is less than 0, then in that case you'll have a perfect transmission. That means your ray of light can transfer very perfectly to the other side of the of this metamaterial.
So A eta can be negative.
Yeah, exactly. Yes. So of course it does. So this is just the homogenization part. So we have the entire problem is defined is categorized into scattering problem as well as the upscaled problem. So,
with respect to various theories presented, the basic estimate falls down. Yeah.
Yes.
And afterwards,
so we are using some results from complex analysis, and so I can show you that paper. And there we can be able to obtain some L2 bound for gradient of U eta. It is possible to obtain that bound, and based on which we can talk about the two-scale convergence.
But this using this, you get this reflection of whatever.
Yes.
Refraction.
Yes, that's the perfect.
Opposite sense. Yeah.
Yeah, that's the perfect transmission. Yes, when you assume that
perfect transmission.
Perfect transmission.
Well, I mean, the theory part, that's what he's asking.
No, it would still work.
Other youngsters also curious to know what happens.
Oh, okay. So I did not include that part, but if any one of you are interested, can send me an email. I can forward that paper, and we can have a look how the scheme is working. No. This is motivated from more like some beam is passing through some semiconductor device, some kind of beam, or weighted what? Weighted data. We have a source term and we have the image, yes. I do not follow what you are saying. I'm sorry. Okay, that will be fine. All right, and that was the so from material science point of view, these are the 5 models that I worked with, and I mean we are still working on further generalization of these models. So first of all, the diffusion-reaction equation system that I showed initially at the beginning of this talk. As I said, that for different diffusion coefficient, the existence of solution is not known. So what we can say that say about when the diffusion of coefficients are different. So that's the first generalization one could make. The another one is instead of having how to say Neumann boundary condition or flux condition, if you alter the condition, that means if you say that this is our domain, let's say omega. And say here you have the Neumann or flux boundary condition, and on the other part you have the Dirichlet. So this is what I mean when I talk about mixed boundary conditions. So you have Dirichlet boundary condition at one part and the normal boundary condition on the other part, and then the regularity of the solution will be lost. Then this maximal regularity technique would not work in such situations. So what can we say about the existence of solution? How we can generalize the concept of maximal regularity to have the existence of solution? And invariant region in what sense?
That the solution takes a particular sector in the state space.
Particular sector, like a smooth domain or something, or ellipsis domain?
As the time varies, the solution values vary, but they all lie in a certain region.
You mean the
Your initial condition at that region.
Okay.
But the solution in future evolution also lie in the same.
Oh, that I don't know. I have not checked it. And third generalization could be, so when you incorporate both precipitation and dissolution in the model, and when both the, when the boundary is also moving, so then in that case, whether we can talk about the global solution or how to say unique solution and things like that. So these are few generalizations one can make with that system of diffusion reaction equations. And that's the overall overview I wanted to give you, which I sort of dealt with in the past. And with that note, I would like to thank you for your attention.